Hello. We are doing a discrete mathematics and its applications problem. My book is a 7th edition. It's by Kenneth, Rosen. So in the 7th edition, this is chapter 5.1, question 32. This is a division problem. I love division problems. It says prove that 3 divides n cubed plus 2n when n is greater than or equal to 1. So n's are integers here. They're not real numbers. So the first thing we maybe look at is what does it mean to be divisible? And for integers, divides is a very specific meaning. So let's write out the idea. Let's say x divides y. And this is the terminology, or the notation means divides. A little horizontal bar. So what does it mean when an integer divides an integer? Well, first thing is that it divides it evenly, meaning there's no remainder. More particularly is we can write y as an integer multiple of x for some integer k. So if I say 3 divides x, what we're saying then is x can be written as an integer multiple of 3. And you can see there's infinitely many x's where this is true. 0, -3, -6, so on, +6. So that's what it means to be divisible by. If x, let's say 3, does not divide x, and that's the little slash, it looks more like a plus when I write it out, but it's not divides. So this will say is not divides. We won't be using this in the proof, but just to give you an idea, this means that I can write x as an integer multiple of 3, but some remainder will be left over. And this remainder will have to be smaller than k and greater than 0. Or I should say 3, not k. But essentially, this is true in division. So we won't be using the notion of not dividing. We will be using the notion that something divides something. All right, so back to our proof. We're going to prove by induction that 3 divides n cubed plus 2n. And like any induction proof, we start with a base case. So the base case here is the first n, this would be true. So n is greater than or equal to 1 means we're doing the p of 1 case. P here is the statement itself. P is n that 3 divides n cubed plus 2n. And so we're checking to see if it's true that 3 divides n cubed plus 2n when n is 1. So let's look at what this is. When n is 1, this is 1 to the third plus 2 times 1, which is 1 plus 2, which is 3. And indeed, 3 does divide 3. Now, 3 means that 3 is equal to 3 times a multiple, or 3 times some integer, and here we know that k is 1. This isn't necessary for this proof, but just getting more comfortable with what divides mean. So the base case holds. So we're going to move on to the inductive step. In the inductive step, we're going to think of as being the PK case, or, well, the induction hypothesis is the PK case. So the inductive step is the assumption that our statement holds for some k, and then the pk plus 1 case is what we're trying to show. So the first thing we're going to do is the pk, or in other words, assume that 3 divides k cubed plus 2k for k greater than or equal to 1. That means we're assuming this is true up until some value of k. And this is called the induction hypothesis. I like to write IH. I like to put it in the proof, so I remind myself that I use the induction hypothesis, which is important in induction proofs, because you want to use the induction hypothesis. If you haven't, you most likely made some assumptions you shouldn't have, or the algebra is wrong, or something went wrong if you get to the same conclusion that we will. Or most likely, you won't use the induction hypothesis and you'll get stuck in some loop where you're making assumptions you shouldn't. So this is the induction hypothesis. This is what we're assuming to be true. Now, I like to write down what we want to show. And I'm going to do that literally by writing we want to show. And we're showing the p k plus 1 case, or the next term, the next integer after k. I like to write this literally. You don't have to do these necessarily, these steps. I find that when you're starting, that these are helpful because induction proofs become somewhat algorithmic in this way. So this is what we want to show. We're not assuming this is true. We're trying to show this, or I put the question mark there, that k plus 1 cubed plus 2 times k plus 1 is divisible by 3. This is what we want to do. This is what we're trying to accomplish. And we're going to do that by looking at k plus 1 cubed plus 2 k plus 1. But what is this? Well, let's multiply it. I'll write it literally first. You can see that we're multiplying k plus 1, the binomial, 3 times, and we're going to add it to 2 times k plus 1. So if you need to review polynomial multiplication, we have a video for that. I will link it in the description if you need some review. So I'll do this step by step. Again, in your proof, if you're write-up, if you're handing this in for a class, or if you're just wanting to write a book on all the induction proofs that you can think of, you don't necessarily have to include all these steps. I like you just to remind folks. And I'm going to FOIL, again, that's in the review, these two polynomials, which is k squared plus 2k plus 1, first, outer, inner, last. And I'm going to add that. And I'm going to distribute this. That doesn't even, not much legible, huh? So this is by distribution. I'm multiplying each term by 2, so that gives us 2k plus 2. Okay, so I'm going to multiply this binomial by this trinomial, and I do that by multiplying each term by k. So it becomes k cubed. I'm doing the k here. So k times k squared is k cubed. K times 2k is 2k squared. And k times 1 is k. And then 1 times k squared plus 2k plus 1 just gives us the polynomial 2k, or k squared plus 2k plus 1, plus 2k plus 2. Okay, so we have this long polynomial with a bunch of k's. Now, the thing we're taught in college algebra is to combine like terms at this point and then simplify. But let's resist that urge. So resist, simplify. The reason is because I want to use the induction hypothesis. And the induction hypothesis tells us that k cubed plus 2k is divisible by 3, right? Let's recall what that is. That's up here. If I want to use that, I want to be able to gather terms here. And I see I have a k cubed and I have a 2k, right? That was in the induction hypothesis. So I'm going to group those. I'm going to put the k cubed plus 2k together. And then we're going to just group the rest of this stuff. So 2k squared plus k squared. And I'm grabbing like terms and putting them next to each other. So we have k plus 2k, and then we have 1 and 2, so plus 1 plus 2. Again, these are perhaps unnecessary steps for your purpose, but I know when I assign problems to students, I love to see all of the work. You'll always get additional points if you are doing everything that you need to do, but maybe made a little misstep. The less you write, the less possibility there is for those kind of points. If you are on a point system, in the United States, most universities, that's how they operate. Assign problems, we do the problems, we're assigned points. I'm not too familiar with other systems around the world, but I guess it's somewhat universal that you can get part of a problem, right? So let's notice on this second term, 3k squared plus 3k plus 3, each term has a 3, so I'm going to factor out that 3, which leaves us with a k squared plus k plus 1. Now, by the induction hypothesis, again, we said that k cubed plus 2k is divisible by 3. And what we said was divisible by something is equal to a multiple of it. So we can write k to the third plus 2k is equal to 3 times some integer. Let's say m. I'm just picking a letter. You don't have to use m. M is just an integer. So k cubed plus 2k is equal to 3 times some integer. We don't know what it is, but that is true because it's divisible by 3. So we're going to replace k cubed plus 2k with our 3m so that we are left with 3m plus 3 times k squared plus k plus 1. I'll write an equal sign here. So now you see we have two terms. Both terms have a 3 in them. So I can factor out a multiple 3. That leaves us with m plus k squared plus k plus 1. So what is this? What is this underlined portion here? Well, this is an integer. Anytime you add integers, you get back an integer. If I square an integer and multiply, I get an integer. So m plus k squared plus k plus 1 is an integer. I could rename it. So let's rename it. Maybe it's clearer at the end why this conclusion will be true. So I'm naming this integer. I'm going to name it p. So if I replace that, that means this whole equation is equal to 3p, which means what? Well, any multiple of 3 is divisible by 3. So 3p is divisible by 3. Where did this 3p come from? It came from k plus 1 cubed plus 2k plus 1. So that is divisible by 3. And that's exactly what we wanted to show. We wanted to show that the next case, the k plus 1 case, is divisible by 3. So that's it. We are done. Therefore, n cubed plus 2n is divisible by 3. I always write both things, QED or a box. I like the box. My boxes don't look like boxes when I write them, but that's it. That's the end of the proof. So like any induction proof, we had the base case, the inductive step, the induction hypothesis, then what we want to show, and then the steps to show it. So go back and review if you need to, but that's it. Thanks for watching. I hope that you got everything you needed to out of this, and let us know if there's something you want to see or any corrections I may need to make. Have a good day.